Hello everyone, it's November the 8th. So first of all, the elephant in the room, yesterday's super duper difficult question, alright? It's a medium one, but oh my lord, is it difficult. Okay, so I'm going to pull it up. I'm not going to go into great details, but that is a difficult question. So if you guys remember, it's an array of numbers, and we have repeats, and we have everybody else has repeated 3 times except for one value. It's only 1 time. So we need to find that one value, and it has to go in on, have to run it on n time. So the post on the discussion is very good. It's long, it's detailed, amazing algorithm. It's like this, right? It's like this. But I'm not going to talk about this. This is a little bit too difficult to go through in a short period of time. But the basic idea, we can expand it. It's like not using bit manipulation. We can use this way to do. So the idea is every number can be represented by a 32-bit integer, right? So what we want is counters, 32 counters. Each counter is responsible for 1 bit. Right, 1 bit, one of the 32 bits. And as we go through every number in a given array, we're going to count, right? We're going to count on each bit the number of occurrences of 1, right? So if a new number comes in, we're going to scan through all 32 bits, and if a bit is a 1, then the counter corresponding to that bit will increment by 1. And the key is, if we have all the rest of the values repeating k times, right? Then if the counter goes up k times, then we will wrap back to 0. So the counter will never go above k. It will just keep incrementing to k and then roll back to 0. Increment to k, roll back to 0. And p is the number of times that the value we want, right? The single value we want, the number of repeats I have. And if you see, this is a generic version. So we're talking about the rest of the numbers repeating k times and the target number repeating p times. And there's one more important thing to notice. K and p has to be coprime. So as we making the counter, we count to k, and then we revert to 0. And if the bit is itself a 0, we just ignore it. We don't count. We only count the ones. Now, we go through every numbers, right? It doesn't matter if it's k repeats or p repeats. We go through every one, and at the end, we have the values in the counter, right? Have a bunch of values in the counter. It must be that for the p repeat value, if in that value, it can also be represented by the 32-bit integer. In that value, all the ones, all the 1 bit in the p repeat, the target number, all the 1 bit must counted p times. Well, of course, we are assuming p is smaller than k, but it's also okay if p is larger than k. Then we just do p modulo k times. So the actual value is always smaller than k, right? So the 1 bit in the target value must be counted p times. And everybody else, I don't care, right? Everybody else will not be counted p times. Everybody else will be counted whatever number of times, but because we have this wraparound, so everybody else will actually be counted 0 times, right? If you think about it, it makes sense. Because if we say the second bit of the target integer is a 1, then as we count, all the other numbers, right? All the other numbers, if they have a 0 in the second bit, we never count them. If they have a 1 in the second bit, they always repeat k times, and once we count k times, they revert back to 0. So all the other numbers who has a 1 bit on the second position, they will always count to 0. So the only thing that will not count to 0 is the target value. So that 1 bit will count p times. So now we have a bunch of counters. We have 32 counters. Some of them have counted p times. Some of them have counted 0 times. So what is our target value? So we know the target value must have 1 on all the positions that are counted p times. So we just search through, we go through counters, right, one by one, and for each counter that is equal to p, well, more specifically p modulo k, then we know that is the position that must be a 1. So we can see that is the, yeah, we can actually go through the algorithm now. So I know what. Wait. Let's go through the logic first. So yeah, we go through all 32 counters. We find the position that has counted p times, and that must be a 1 in the actual target number. And then we find all the ones, and everybody else will be 0. Then we can turn that value, into the binary, and the binary value we turn that to integer, and then we're done. And because it's a generic version, right? So we can actually change k and p. It doesn't matter. We can say 3 repeats and a 1 value repeated 7 times, which is completely fine, right? Completely fine. So now into the implementation. Now the implementation is a little bit complicated because of Python's handling of negative values. We're going to go into that later. So first we establish all the counters. We have 32 counters, and we have a pp, which is p modulo k. So pp must be co-prime with k and a smaller than k. Now this is very important because we are assuming, right? We are assuming that the target values will repeat smaller than k number of times. So we have to do this. Now here we have a mask. It's called two's mask. So this is used to handling a two's complement. Now in Python, it has a very interesting implementation of negative values. So this is basically because Python doesn't restrict signed integers to any given number of bits. You can, like in Python, the numbers can be gigantic, right? So because of that, if you type binary -2, and you will see it's -10, right? Instead of 2's complement based on 32 bits. Now because of this, if we just use this the negative, because the input values can be negative, then we want to turn the negative values into the binary version. And if we don't do anything, then the binary version will be a negative something, and that breaks our code. So we need to turn into its 2's complement form. Now to turn into 2's complement, one way to do so is we can establish a mask. If you see that, this is the largest value in some largest value. It's just 32 bits. Each bit is 1, right? So if we AND the value with this mask, what we get is the 2's complement of the negative value. So if we can say -2, right? If we AND, and we say 1 left shift 32 times, and then -1, right? And then we take the binary of this, and we'll see that is the 2's complement of -2. There are other ways to do so. I believe we can also do 1 left shift. I think we can do 1 left shift 32 and just -2, right? That one shall also give us the same. Yeah, that also gives us the same. So this is basically going back to the definition. So what is 2's complement, right? So why do we need 2's complement? So we use 2's complement to represent a negative value. And for a 32-bit signed integer, the maximum positive value is 1 to the 31st -1, right? And so the leftmost bit is reserved for all the negative values. So for all the negative values, what we are doing, right, is actually using the larger values, like a 1 left shift 32, right? That's the biggest value. We'll use that to minus, right, to minus the negative value, and the results will be within. So 1 left shift 32 is 33 bits, right? So 1 followed by 32 zeros. And if we use that to minus, or we say plus a negative value, that value will be 32 bits with the leftmost bit being 1. So we are using that to represent the negative values, and that, so we can either do 2's complement to reach there, or we can do the large value minus the other thing. So in fact, I think it will be easier to have us, yeah, we can actually just say 2's, right? And then we can just say 1 left shift 32, and then instead of 2 to the end, we can just say 2's, let's say, just say 2's, right? And for here, it'll be 2's minus n, right? 2's plus n, because n is a negative value. Oh, hold on. We cannot do that because n could be positive. Oh, yeah. So, you know what? No, this has to be this way. I just realized why we have to do it this way. Because we are handling negative value and positive value at the same time. So, for positive value, we end the 2's mask and nothing changed. So, negative value will get to the 2's complete version. But we'll see it again. So, limit is the largest positive integer available in the given question. The given question is 2 to the 31st minus 1, so that's our limit. So for each value, we turn this number into its binary form. If it's a negative value, we go for the 2's complement, and we go 1 by 1, right? And then if the bit is a 1, then we, on our counter, plus 1. But we have this trick, right? We have the modulo, so we will not go over k. So we increment the counter by also modulating k. So once we're all done, right, we run through every value. It's on because we go 32 times here. So it's 32n. Once we're done, we have the counters, right? Sum of counters will have the pp count. Sum of counters will have the 0 count. So we basically go through every counter, and if the counter is pp, that means that position, that bit position, must be 1 in the target value, so we solve for 1. Otherwise, it will go for 0, right? And then we'll join them, right? We join them into a string, a binary representation string, and then we call int on it with 2. Now, this is the interesting part, right? Because if you see, let's say binary str is equal to, let's just use the same thing, right? Let's use this. Actually, I cannot copy and paste, but it's fine. So I'll just say 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Oh, that's pretty stupid. I have to do this. So that's BSTR. If we go int BSTR and say we're into binary, this is the value. You guys see is 4294967 which does make sense because Python doesn't have a 32-bit integer. Python has the integer is unlimited. So if it's unlimited, this is not a assigned like value. This is just a giant value, right? So if we return that immediately, it's going to be wrong. Therefore, the result, when we turn into the integer, we have to check if it's larger than the limit. Smaller than the limit, everything's good. If it's larger than the limit, that means we need to return a negative value, right? So how do we turn this into the negative value, which is negative 2? So we use the trick of 1 left shift 32, which is the bigger one, the 32-bit, 33-bit value, right? And we use that to minus, we can say int bstr, and then 2. So this will give us, well, we have to put this. This will give us, oh, it's actually, it's the other way around, my bad. So it's this, because we need to get a negative value. And this is smaller than this, my bad. So that will give us negative 2. So that's why we have to do res minus this. And then this is the generic version. So that's the, yeah, it's very, I mean, like you breaking down like this, it kind of look very straightforward, but yeah, it's impossible. I wasn't able to figure it out. And if I want to talk a little bit about this, all I can say is this one simply, so instead of setting up 32 counters, right, we are using 32-bit integers. And if you think about 32-bit integers, each bit, right, can be considered as part of a counter. right? So we have 32-bit integers, and then we are breaking down a counter into n bits, right? So each bit is represented by an integer. So x1 means is the first bit of all 32 counters. x2 means the second bit of all 32 counters, right? And depending on how large the k is, the number of bits is log 2k, right? And then the difficult part is because we are breaking down the counter, each counter, into bits. So we need to like increment instead of just say +1. We have to figure out a way to increment using bit manipulation. So basically, these are the increment, right? And this is the modulo. So the idea is the same. We'll increment, and then we'll modulo if it hits k. And when we're all done, we're gonna have the counter. And the counter is represented by all the first bits is on x1, or the second bit is on x2. Now the beauty of this is within the counter, if we break down into the bits, it will have 0, it will have 1. Then it's guaranteed that the 1 bit, right? The 1 bit must come from counting the 1 bit in the target value. The 0 bit can be counting 1 or it can be counting 0, we're not sure, but the 1 bit, the reason that certain bit in the k is 1 is because we are counting the 1 bit inside the target value. Therefore, all the 1 bit, like x1 or x2, whatever, is a 1 bit, that integer, that bit represents all the 1 bits in the target value. And because we have 32 bits inside each x1 or x2, so that thing is actually the answer. Now, it's very bad explanation right now. This one requires deeply, it requires you to sit down and then just go through that article line by line and appreciate, right? And appreciate how the whole algorithm goes. It's really, really neat. And this is also a generic version, right? It's also a generic version. All we need to do is, like if a k is larger, we just add more bits. And if p is larger, and we say p because p is 1, so we're taking the first bit, the first bit is 1. If p is not 1, say p is 2, then we have 1, 1. So we can take the first one, or we can take the second one. So p can be any value as well. And then we just find the bit that is 1, and that bit, the representation on 32-bit number for that bit is the target value. So yeah, it's amazing that this question is labeled as medium. I mean, coding-wise, it is medium, but for me, it's very, very difficult. All right, so that's the elephant in the room. Now the elephant is gone. We can go for what we have today. Number 96, I've done this before. Pretty sure I've done this before. Yep, back in July the 7th, 2020. All right, so let's say give an integer n, return the number of structurally unique binary search trees, which has exactly n nodes of unique values from 1 to n. Ooh, I forgot how I did it. Let me see. Isn't there a formula for this? I don't know if there's a formula for this, but basically we say we want to find out. Oh, hold on. I actually forgot. Looking at this, right? I mean, one way is just, I don't know, we just build all of them, right? We can build all of them. we can say we pick 1 as the root, right? And then, yeah, we'll pick 1 as root. And then for the remaining, we can pick whatever, right? Whatever is going to be on this. Yeah, we can pick 2, we can pick 3. Yeah, so like we pick 1 as root, and then the remaining value we just go 1 by 1. We can pick 2, go to the left side, and then we're gonna recursion again. Well, I think 2 cannot be on the left side. 2 has to be on the right side, and then we recurse again on 2. I feel like it should be an easier version of this, right? And then 2 is here, so our focus is on 2, and then we have the remaining value. So we just keep building. And once this is done, coming back, and then we say, okay, 2 node is done. Now we're gonna go 3. So we put a 3. Now put a 4, right? So that's 1 as root. So when 1 as root is done, we say, okay, let's go 2 as root, right? So when 2 as a root, we take 2 out. Then what? Then we're gonna go 1. And then we have, yeah, we take 2 out. Then we have the left half and the right half. So the left half, we're gonna build whatever we can build. The right half, we're gonna build whatever we can build, and that's it. And then we take 3 as a root. Okay, so a left half and a right half. And when do we end? Well, this one will guarantee that the tree built is unique. So we can just, at the end, we're basically splitting, right? We're splitting, and eventually, when is this over? When is this over? That's a good question. I don't know. When is this over? Well, the subtree, right? So the left subtree, we can return how many, and the right subtree will return how many, and then added together will be how many we can build. Okay, let's try this. I'm pretty sure it could be an easier way to do this, but for now, let's just handle it like that. Okay. Time flies. It's already November the 8th. And Ole Gunnar Solskjaer is still Man United's coach, manager. How ridiculous is that? How ridiculous is that? Yeah. The team just doesn't seem to be caring, right? Doesn't seem to care. Alright, so on num trees, we need to have a helper. So we call it DFS, right? We call it DFS. And we're gonna say, we actually don't have node. It doesn't have to have node. It's the current value. So value, and we need, actually we don't need value, we need an index. Right, we need an index. Actually, we don't need index. Oh, what I'm thinking. We need, what do we need? We need an index, and then we say that's gonna be, it's actually gonna be a low and a high. We need low and a high. The range, right? Low and a high. This one I'm gonna return an integer, right? So that means given us this range, how many unique trees we can build, right? How many unique trees we can build. In this case, maybe we can also cache it. Anyway, so we're given a range, right? So we're gonna always start from the first, and then blah blah blah. We can obtain a total. So we say if low is equal to high, right? Low is equal to high. What does that mean, low is equal to high? So we are saying we're building just one, all right? It's just one. So that's going to be return 1, right? Else, y we're going to say rest equal to 0. And we're going to say for what? For the root, right? So from low to high, we can pick a root. So it's just for I in range, from low to high, right? We say if I is a root, oh, we also need another thing. If low is smaller than high, no, low is larger than high, that will return 0. Right? So for this, now we can say res plus equal to dfs low I minus 1 and plus dfs I plus 1 into high, right? So rest plus equal to this, that's just the left and the right portion subtree. Now once we're done, all of this is done, so rest is done, and then we'll go to the next one, and next one. And once we're done, we're gonna return rest. And for this, I need, let's say, from func tools import LRU cache. Oh, we just did an LRU cache problem. I still remember I was very good. LRU cache, I think we can say max size equals none. Alright, so that's that. Then we're going to return dfs low is 0. Is low 0 or low is 1? High shall be n. Actually, it doesn't really matter. I can just say 0 to, well, 1 to n. Okay, how about 1 to n? Yeah, be 1 to n. Alright, let me give it a shot. So I say 3 shall give us 5, and 1 shall give us 1. 1 shall give us 1. This is n, num trees n. I run it. Oh, it's not max. Oh, I spelled it wrong. Max size. Uh-oh. Uh-oh. We have an issue. We have an issue. What is this? And 1 to n. The result is 6. Huh. This is 1, this is 0, otherwise it's this. And then we say for I in range, I can go from low to high. Yeah, we need to include the high. And then low I minus 1. Yes, and that will return 0 initially. And then this will go to I plus 1 to high. Okay. And rest plus equal to this, and now return rest. Why is this not right? Alright, I need let's see what I need. I need to print. So on the print, low, high, and rest. Okay, let's see. Low is 2, high is 3. I have 2. Low is 2, high is 3. 2 and 3. We only have 2 and 3. I have 2, so 3, 2, or 2, 3, right? That makes sense. 1 and 2 have 2. 1 and 3 have 6. Huh? We have 6. That is Yeah, so it's a 1, right? Yeah, I can go through this. So we have low is 1, high is 3. And then I'm going to have 1. Starting from 1, 1, 0, that's 0. And then 2 and 3. So 2 and 3 give us 2. So rest plus equal to 2. So that gave us 2. That's the first 2. Now we're going to go I and go 2. All right. So I is 2. So the left is going to be 1, 1. Right, and be 3, 3. Oh, that is a problem. 1, 1. That's one way. That is also one way, which means if the left is one way and the right, oh, shouldn't we? Oh my God, I think this is multiply. Well, it's larger equal to. It's one way. That just means it's one way. All right, I just mean it's one way. Yeah, it's multiply. So the left we have 3 ways. The right we have 2 ways. So altogether it's 8 ways, right? And if the left is nothing, that's one way. It's one way. That's why this looks more promising. All right. We are going to run the test case. Let's just go 4, 5, 6, 19. Why not? And we are correct. So I think we can submit. And we got it. So not too shabby. All right, let's see. This is our last submission from the previous attempt. I'm pretty sure it's similar. Okay, let's see. Yeah, I see. This is bottom up. All right, bottom up. There's a top down. Of course, top down. Top down is easier to reason with, right? Top down is easier to reason with. Now I'm gonna go top down. So just LeetCode 96, right? 96. Top down DP, right? Top down DP. O(n) squared. Is that O(n) squared? What is runtime? Yeah, O(n) squared, because we have low and high. We have all the combination. Oh, that's not O(n) squared. That's all the combination of low and high. Yeah, that is O(n) squared. So O(n) squared, and we run it. I think what 32, 67. Okay, so that's it. I mean, I don't think there's anything more about it. Math one-liner. Oh, I remember. Catalan numbers. Yeah. Catalan numbers. Yeah, whatever. Catalan numbers. I think I read this one, right? In GN. Yeah, look at this. This is the one. Is this O(n)? Yeah, it is, because I cached. Right? I cached every single pair. But actually it's not. Every single pair is how many pairs? It's n choose 2. N choose 2 is O(n) squared. N choose 2 is O(n) squared. All right. I we'll stop right here. I like how this one is, playing in my head. So that's that. All right, we're gonna shut this down. Let's roll another one. And we are doing it sequentially, so we're no longer doing it random. That's no point. What's the point of doing it random if our purpose is to do everything that we can, right? So all we're going to do is row a median, go to the second page. So we handled everything here. So the first one is this one, fraction to recurring decimal with only 23% passing rate. I mean, this is hard. Oh, people hated it. Oh, wow. People hated it. Absolutely hated it. Given two integers representing the numerator and the denominator, return the fraction in string format. If the fraction is repeating, enclose the repeating part in parentheses. If multiple answers are possible, return any one of them. The length of the string is less than 10 to the 4th for all the given inputs. 2 to 3, 4, 1 to 5. Okay. So we're not cheating, because cheating means going to the Python library. They have fraction, but we can do that. You know what? That doesn't matter. But I need to read the documentation. I don't know, like Python fraction. I mean, if it's a real rational number. Think about the real life scenario. If you have to handle this, I'm not going to write one myself, right? It's definitely going to go with this. We can do numerator, denominator. Okay, what can we do? We have a fraction. Can we have denominator as integer ratio from float, from decimal? We can go limit. Actually, there's no way to represent the actual thing. Really? It returns to a fraction, but I don't think you can do anything about it. No, I don't think so. We have to do long division, I think. Yeah, this is not gonna work. This is from float. This is from decimal. Well, maybe decimal has a implementation. I don't know. Decimal object. Decimal. Just as integer ratio. It's tuple, canonical. Compare total, conjugate, exp from float. Wow, that's a lot. Decimal has a lot. I mean, maybe there is a way to do it here. Convert to string. Oh, I was using engineer notation. Don't we have like two string? We have two scientific string. Let's try this. Hey, who knows? Maybe this one. I never tried it. So decimal. Look at this. Decimal. It returns this. Precision. We can get precision. If we can give precision, you wanna try? Yeah, I wanna try. Let's go here. So let's say from decimal import decimal, right? I'll say decimal 1 divided by 7, right? Decimal 7. Oh, I forgot to do precision. It says the precision is less than 10 to the 4th for all the inputs. Can we do 10 to the 4th for the precision? You can say what? Get context, right? We say get context dot precision equals 10 to the 4th. And then we do this. Oh, geez. Yeah, it's possible. But we need to turn that into a... But how do we identify, how do we know the repeats? So we need to scan for repeating. Now that is not easy. So we scan. I mean, one, 4, 2, 8, 5, 7, and 1 again. Okay. 4 to... even if I have this, how do I identify the repeating part? Do we have something with the repeating? Maybe if we say dot to, wait, what's this thing? Dot to engineering string. Let's try it. Who knows? So it's going to be this dot to engineer string, huh? I don't think that's, hold on. Nope. Okay, so I mean this will be the same. I can use this to obtain, or I can do the long division, right? But in the long division, we will know. We will know when the repeats happen because one of the quotient, one of the remainder will repeat. So that's when we know. But in this, it actually is harder, right? We're talking about having a string that we know must has a repeating pattern. And how do we know what is repeats? Exactly. How do we find the repeating pattern? I mean, we can go scan, window 1, now repeating, 2, now repeating, 3, now repeating. Ah, that might work. Might. How do you know it's the smallest repeating that's gonna work? They will create some test cases that definitely, right? You don't know, right? You don't know. You have to go end up with binary search, right? We go the gigantic. Oh, then that will be repeat. Yeah, if the gigantic repeats, what if the gigantic doesn't repeat? See, that is the problem. Yes, exactly. That is the problem. We don't know. We don't know the size of the repeating, right? So if we want to try, And you cannot try. Like you say the first, let's say I have repeated twice. How do you know it's only repeat twice, right? So you have to go, like if it doesn't repeat, you can keep trying the next one. If it does repeat, you will have to go all the way to the end, right? You have to go all the way to the end to see all of them are repeating, right? And you find the first one that goes all the way to the end, and that should be the one. So in that sense, we can do this, but I'm not sure the runtime will be any good. Like seriously. But 10 to the 4th, right? 10 to the 4th, maybe it's fine. I'm going to try this one. I mean, it's not what's intended, but hey, anything make it a bit easier. A little bit easier. Alright, let's see. So when we do this, after this, we need to say from, we just import. Let's just import decimal. Alright. And then we're gonna say, oh, we can put context here. Yeah, what's context? You can give us any example of this context thing. Context equals none. Context equals none. What is this context? Hold on, let's see. Context. We have get context. Oh, I guess one of these things. Oh, get context. I see. Nah, that's fine. Let's just do this. So first of all, we're gonna say decimal dot get context dot precision equals 10 to the 4. All right, that's the largest. And after that, we're gonna say dstr decimal string equals decimal dot decimal numerator divided by decimal dot decimal denominator, and the whole thing dot to engineer string. Is that how it's spelled? To ENG string, no R. Okay, so now it's to string. Now is the time to find now I need to find the decimal point. Wait, is the numerator larger? It does not look like. Okay, so we need to find the decimal point. Right, so I'm going to say I equals 0. Right, for I, a while dstri is not equal to the decimal point. What is I actually don't know. How about integer? What's the result of integer? I gotta have a example of integer. Decimal this. Shoot. I actually don't know. Well, in that case, what if we go float? Oh, I just realized something. I don't know. I need to test. So import decimal. I'm gonna do this. All right, string. But I'm gonna change. Let's say 1. Right? The integers 2. Decimal has no attribute decimal. Oh, we have a typo that I didn't even know. Oh, DSTR. Is it 2? So are you saying that if it's a integer, we're gonna have no problem? We have no problem. If it's integer, we have no problem. Okay, so while this is not equal to this, why don't you just use index? All right, I think we can do dstr.index dot. It's going to give us, oh, we're going to give not found. Try, right? Let's try. I equals dstr.index. This, right? And then accept value error, and return dstr, right? That's it. Because we can just return that by itself. Okay, now we found it. Now we just need to find if there's any repeats, right? So how do we find repeats? Well, we just said we're gonna go repeat. Hold on. What if we do 2 divided by 4? What's gonna happen? 0.5. Huh. Therefore, I should do this plus 1, right? I should do precision plus 1. And I say if len dstr, right, minus 1, that's the last position, minus I, right? So I want to know the total, the length. How do we know the length? The length is going to be 1 is 2, 2 minus 1, 1, 2, 3, 3 minus, so it is this minus I. If this minus I is smaller, the position is 10 times 4 plus 1, right? If it's ultimate, it will definitely be longer than 10 times 4 plus 1. That's what it means by the precision. So if it's smaller or equal to 10, then do 4, right? Then we just return the str because that's not repeating. Otherwise, if it's repeating, then we're gonna go for length. Now so repeating length for length in range. No. While length equals length is 1. Alright, length is 1. So while length, while true, right? While true, so we say the window is 1. So what we're gonna do is we have I. So the first position, so j, it should be I plus 1. So we're gonna say if of a window, so we have to go the next one, right? So we say if dstr, right, from j to j plus length, so j plus 1 plus length. Well, it shouldn't be plus length plus 1. Because if j is 1, the length is 2, 1 plus 2 is 3, so the 1, 2, 3. That's 3, so in the plus 1. If this is not equal to, right, dstr. The next one is going to be j plus the length plus 1, 2, j plus 2 times length, right? So j plus length plus 1. So that would be plus length plus 1, so plus 2, right? So if this is not equal to, then we're going to do length plus equal 1 and continue. Else, if they're equal, then we know the potential is equal to this, right? So we have the potential. So now we just need to loop through to see if this can match. And how do we do? We're going to say, we're going to do k, right? We're going to do k. We have to go, j changes. J has to be here, right? So now k is equal to, let me say for k in range, right? J plus 2 times length plus 2, right? 2 times length plus 2. That's the starting point. End point will be len dstr, and it will be length. There's not length. Alright, so we do this, and the next one will be this plus length. No, that'd be length plus 1. So for k in this, we say if dstr k to k plus length plus 1 is not equal to potential, then we're going to break. Alright, then we say else, we say length plus equal 1, and continue. Otherwise, if we don't break, then we're going to return the actual value. So what is the actual value? Well, the actual value is going to be the potential, right? The potential is right. So we're going to do dstr to I, right? That's that. Oh, actually I plus 1, and plus potential. It feels very convoluted. And I just realized even if this passed, I'd still have to go with the other approach, the long division approach. Because this is kind of cheating, right? But actually I don't say, because it's not that simple to get. Oh, hold on a sec. I just realized something. Some don't repeat at the start. Right? Did you remember that? Like maybe like divided by 13? Is that a 1? I remember something don't go at the start. Oh shoot. That is not gonna bode well. I think it's 13. Oh. Let's do like 10. Oh, dot position 10. But equals 10, right? Now this one does repeat. Yeah, I remember something does not repeat. Like 10 probably too small. 20. Something has like start repeating. Is that a 1? What's the pattern? No, it's 0, 5, 2, 6, 3. No, it's still repeating stuff. Wait, oh, is there? Sure, there is, right? Say 1 divided by, let's do 1 divided by 7. I think I can construct 1. 1 divided by 7 is this. So we have 1, 4, 2, 8, 5, 7, right? So it's 1 divided by 7 equals 0 point this. So how can we can add, let's say we add a 3 to it, right? So we add a 3 plus this. So 3 plus this will be 3.142857, and then that's repeating. And then we divide by 10. So 22 divided by 70. 22 divided by 70. Ah, that beat you, man. That surely beat you. 22 divided by 70. Look, it's 0.31425. All right, so this method doesn't work. So you have to, because I always start from the start to try to count repeats. All right, scratch this, scratch this. I don't think this is not worth it. Let's do. And also like you see this, they also rounding. So no. No. Let's do the long division. 22 divided by 70. Holy guacamole. We're going to write a program to do long division. Well, compare first. 22 is smaller, so the first one is 0, right? And then we add a decimal point, and then the 1 we're going to multiply by 10. Now it's 220, and then with the div mod, it'll give us 3 and give us 10, right? Give us 10. And then we're going to multiply by 10 and div mod. You know what? Actually, this is not that hard. I just realized. It's trying to go find a shortcut, and the final is actually the I think the other difficult part is we need to know where to put the parentheses. Where to put the parentheses? So we can keep track of the indices, right? Yeah, we can keep track of the indices. I think that should be fine. And 4 divided by 333 give us 0.012. I think that they're intentional, that they didn't put the other situation there, which I just created, which is this glorious 22 divided by 70. Right? That is going to be 0.3, and then parentheses 142.857. Right, so that's the one we need to do. Okay, let's do this. It's fine. Thermometer. So we're gonna say d equals to n equals numerator, right? Yeah, n equals to numerator. And while true. Everything okay? That's while true first. All right. Oh, and then we have res equals. What do you want to do, res? Just a string. It's fine. We can build a string up. It's fast. So while true, we're gonna say if the div mod, right? It's always gonna be div mod. So div mod. So we can have quotient, a remainder equals div mod div mod n and a denominator, right? Then if q is not equal to 0, no, this is the first round, right? The first round, we can always do the first round. We always need to do the first round. Okay, let's do this. Quotient and n equals div mod numerator denominator, right? And the rest is equal to f q, right, as the quotient, and dot. Now we have n. Now we're going to do this, always n times equals to 10. And then we do div mod again. All right, we div mod, then we have a new n. But how do we keep track? How do we keep track? We need a dictionary. Right? We need a dictionary. So we need a dictionary to track the let's call it hash set, hash map. Right? The dictionary, and dictionary, the current, right? So the current n is going to be, current n will be responsible, right? The current n will be responsible for the first. Yeah, we can multiply by 10, and we record the multiply by 10, because if we do that, then the position, which is fine. We can just say hash map n equal to 0 position, right? And then n times 10, which we actually don't need to do n times 10. We can just do n times 10 here. So div mod, we have a q and n, right? Then what do we do? Right, then what do we do? So that's times 10. So n, we shall check. We shall check. So while n is not in hash map, now we add this, and then we do the new one, right? So n is not in hash map, so the quotient will be definitely needed. And then we just go res plus equal to str q, right? We can do that, and then we go back up with a new n, and if the new one is inside, then we break out, right? Then we break out, and that's actually not. That has to be. We need a counter. We need I equals to 0, right? So it would be I, and then I increment, right? So once we're done, once n is inside the hash map, then we know we need to jump out. Now we have the n, right? So the current one we don't do anymore. So the current q not in. So we just need to find the previous q. So I think we can directly return res up into hash map n plus 1. Hold on, no, not plus 1, just hash map n plus 1 plus a left parentheses plus res hash map n to the n plus right parentheses. Okay? Now we can see if this one works. Too many values to unpack. what we have is numerator, denominator. I haven't even changed this thing. Jeez. Come on, man. Fraction to decimal. Numerator, denominator. That is not what I expect. Okay. There are issues. There are issues. What are the issues? First of all, we have the thing I just going before, so that's not good. So there are a lot of things to deal with. Oh, I is not 0. I is going to be len res, right? Now we just need to handle the one that do not repeat. Why would they not repeat? Well, they not repeat because n is a 0, right? N is 0. So what we need to do is to see if n is 0. So when I turn this, if n is 0, we just return res. So we return res if n is 0, else we'll return this. Okay, we do. Holy guacamole. What is this? On the right strip. No, I don't like right strip. So while n is not equal to 0, how about that? And n is not in this. So now they can't even come in, right? And then all we need to do is, if n is equal to 0, and then only thing need to handle is the decimal point for the integers, which means we need to change this. We can do this, right? We say if n is equal to 0, then we just return strq. Problem solved. Otherwise, we do this, and blah, 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 and then we do this. That's it. That is the solution. No decimal needed. No decimal needed. Submit. Decimal is not needed. Ugh, I think we have a wrong answer. Oh, negative value. What the heck is... Oh, shoot. Negative value. Come on, man. Negative value. Seriously? -1, 2, -0.5. What do we get? Gosh. Oh, it's a div mod. Jesus. Div mod. So we need to also have the parity. So parity equals to numerator times denominator is that larger equal to 0, right? So if larger equal to 0, the result will be positive, otherwise the result will be negative. So then we can do ABS. Yes, we do ABS. Then we do ABS. Right? Can we do this without? Yeah, but that's the implementation of div mod. Right? We don't want to mess with that. So we're gonna say return this if positive is pos. So if is pos, else we're gonna do negative q. That's not the strq. So stupid. I just do this. And these are fine. And then we're gonna say, oh my god. Let's do this. Res equals if n is not equal to 0, then res equals this. And then we return res if is pos, else we do negative, because res is already a string, plus res. Okay. Also, we're gonna test this one as well. Minus 50, right? So we have minus 50 and 8. Minus 6.75. Actually, you know what? I put expected. You know what? I just realized something. It's always one. I'm always returning one smaller, right? So I just plus 1. Plus 1. ND equals to. Nope, I don't like that idea because I want everything to be positive. Everything is positive is the best way forward. Everything is positive. Because if we have negative, that just makes things complicated. All right, let's try this one. Now I know why the passing rate is so low. Because we have something called edge cases. In terms of edge cases, actually, I want to run a few more. That should be return 0. All right. And then we need to do some minus. Let's say minus 4 and minus 33. That should give some positive 0.012. All right, I think this one is solid. Go for it. Come on. Come on. Come on. Yes. Yes, we got it. So, not too hard a question, but the negative cases did catch me off guard. Yeah, forgot about the negative. But the negative cases can be easily handled by checking the it's called parity, right? Is that called parity? What's parity? Whether a number is positive and negative? Equal. Nah, I don't think that's the one we're looking for. So, okay, checking the positiveness of the result at the beginning. And then treat both numerator and denominator as positive values. We perform long division and stop when a remainder has repeated. Also, for each remainder, we keep track of its index in the result string. I wanted to use the decimal library, but the process of finding the exact repeating pattern is much harder than I had expected. Actually, I don't know. I should say. Actually, I don't even know how to find a pattern of unknown size. Actually, I do know, but that's just very slow. That's very slow. Because we have to go, because we don't know how many is non-repeating at the beginning, so we have to go like sliding windows through the entire thing. That is super, super slow. So this one will be, oh, what is the runtime of this? Time complexity, no idea. 24 milliseconds. I wish score 97% ranking. Pretty good. Alrighty. Let's see. Smart people, what is your solution? Oh, so long. Stream builder. See? That's always have to do ABS. Integral part, yes. Fractional part. Hash map. Oh, it's the same idea. No need to keep looking. Alright, that shall be it for today. I will see you guys tomorrow. Adios.